Hi, welcome to my channel. Just in previous video, I explained about the basic information related to spanning tree and the minimum cost or minimum spanning tree. I already explained in a previous video that we can construct a spanning tree using two algorithms. One is Prim's and another one is Kruskal's algorithm. Here in this video, I am going to explain Prim's algorithm, how the Prim's algorithm works for constructing the spanning tree for any given graph. I am going to explain by taking one example. Okay. Now I briefly introduce what is Prim's algorithm. So generally, so what is spanning tree? Once again, I will introduce what is spanning tree. The spanning tree is a subgraph of a graph. So what do you mean by subgraph? That subgraph is the subgraph in terms of edges, not vertices. Because suppose if graph is containing 10 vertices, you must include all 10 vertices into spanning tree. But suppose if graph is containing 20 edges or 30 edges, so based on number of vertices, we must include the number of vertices minus 1 number of edges for constructing spanning tree. Even you include one more edge, which makes cycle. Okay. So what is the Prim's algorithm now? So what is the aim of Prim's algorithm? So Prim's algorithm aim is to find the minimum cost spanning tree. Anyway, which uses greedy approach. Greedy means which always selects min as a criteria. So based on min as a criteria, which always selects the minimum cost edge every time among all the remaining edges. So here we are using the shortest path first algorithm, similar to the shortest path first algorithm for constructing spanning tree. Okay. So here initially the spanning tree is empty because we have not yet included single edge into spanning tree initially. Just we have graph and the tree is empty initially. So here our ultimate aim is we need to maintain two set of vertices. So one set of vertices are maintained with the already included vertices. Another set must maintain non-included vertices. Okay. So here we are going to maintain two sets here. One set of vertices are belonging to tree. Another set of vertices are belonging to graph. Okay. So I have already told you now, the first set contain vertices already included, and second set is containing the vertices not yet included, but which are still there in graph. At each step, I have already told, at each step, we must compare the edges which are formed with the set of vertices which are there in tree and set of vertices which are there in graph which are not yet included into tree. So based on all the edges, once you select all the edges, select the minimum cost edge and include that particular edge into spanning tree. So this is the idea. So idea behind constructing spanning tree by using Prim's algorithm is every time select the edges which are forming with the vertices which are already included in spanning tree with the vertices which are there in graph which are not yet considered in the tree. Okay. So based on all the edges, once you select the edges with the spanning tree vertices with the graph vertices which are not yet included, select the minimum cost edge and include that minimum cost edge related vertex into spanning tree. So we are going to repeat this particular procedure until including all the vertices into graph. Our ultimate aim is including all the vertices into graph every time before including the edge. That particular edge must not perform or form a loop. Okay. I have already told in previous video that we can easily identify how many number of spanning trees are possible. Suppose if the graph is completely connected, then we can directly apply n power n minus 2. N is number of vertices and n power n minus 2 means if number of vertices are 4 and graph is completely connected, then 4 power 4 minus 2 means 16. We cannot always expect the graph completely connected. So in that case, generally we take the formula for calculating the number of spanning trees is count number of edges. Those number of edges C. Suppose number of edges are 9. Then 9C. Then how many edges required for constructing spanning tree? If number of vertices are 10, then the number of vertices minus 1 number of edges are required. Is it clear now? Suppose number of vertices are 9 and number of edges are 20. Then number of edges are 20, number of vertices are 9. Then the formula becomes 20C8 minus 2. 20C8 minus 2 or minus 2 or minus 3, whatever it may be. But we need to identify number of cycles here. So based on number of cycles, then we can frame the formula as total number of edges C, the number of edges required to construct spanning tree minus the number of cycles in the graph. I will show you in example how many number of spanning trees are possible for the given graph. So from that we directly construct one minimum cost spanning tree using Prim's algorithm, because we have one separate procedure. We need to follow that procedure for constructing spanning tree. Straight away we get the minimum cost spanning tree using this particular procedure. Okay. Now suppose if we take this graph, this graph is containing some 6 vertices and some edges. Is it clear now? So here some edges are there, some vertices are there. But if you observe the graph, that graph is containing loops also, self loop and some parallel edges. Self loop is C is containing self loop, and in between A and B there are 2 edges. So those 2 edges are called as parallel edges, and C is having its self loop. That loop is that particular edge is called self loop. We must not contain those type of edges. Okay, na? We should contain only one edge and between 2 vertices, that too minimum cost edge. Whenever parallel edges are there, we must remove parallel edges. We must remove parallel edges. We must remove parallel edges, and we must remove cycle. See here, C is having cycle. C is having cycle. Then remove this cycle, and A is having 2 parallel edges. You must remove 1 parallel edges. That particular edge containing maximum weight. So here A to B, 2 parallel edges are there. One edge cost is 6, another edge cost is 9. Then remove edge 9 and remove C. So whatever the dotted lines I represented below the diagram, second diagram in this. So those 2 edges you are supposed to remove. One is parallel edge. A to B is parallel edge, cost 9 compared to 6. The 9 is greater. And another edge we are going to remove is C self loop. Okay, na? So after removing these 2 edges, then we get this particular graph. Now how many edges are there in this graph? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges are there. Okay, na? How many vertices are there? 6 vertices. Then how many spanning trees are possible? I have already explained na. Number of edges 9. C, number of edges required for constructing spanning tree. So number of edges required for constructing spanning tree is 1 less than the number of vertices. Then I can write this formula as 9 means number of edges. C, 5 means number of edges required to construct spanning tree minus number of cycles. How many cycles are there in this graph? 4 cycles. One cycle is SAC, another cycle is ABC, third cycle is CBD, and fourth cycle is BTD. Okay, na? Then the formula for constructing number of spanning trees possible for this particular diagram is 9C5 minus 4. 9C5 minus 4. So these number of spanning trees are possible. Suppose this graph is completely connected, then we can directly use n power n minus 2. N is the number of vertices. Number of vertices power number of vertices minus 1. If 6 vertices are there, 6 power 6 minus 2 number of possible spanning trees are there. But this graph is not completely connected. Completely connected means from every vertex there must be a direct edge to all the remaining vertices, but such scenario is not there in this. Then directly use the formula as number of edges in the graph C, number of edges required for constructing spanning tree minus number of cycles. Then simply I can write formula for this particular diagram is 9C5 minus 4, where 9 is number of edges, C, 5 is number of edges required for constructing spanning tree, minus 4 is number of cycles. Is it clear now up to this? Okay. So this is the graph after removing the parallel edges. One parallel edge, 2 parallel edges are there between A and B. Now I removed AB, one parallel edge with the cos 9 because compared to 6, cos 9 is greater. And I removed one self loop, that is C is having self loop. Now after removing all this, I got this particular graph. Now my aim is, or our intention is to construct a spanning tree using this particular graph, or on this particular graph construct spanning tree. What is spanning tree? Spanning tree is a subgraph of the graph. Subgraph means you must consider all the vertices, but we consider only edges, few edges. Few edges means the number of edges which are exactly equal to the number of vertices minus 1. So 5 edges we should consider for constructing spanning tree, but you must include all the vertices, all 6 vertices. But before going to construct spanning tree, you must select any vertex as origin vertex or arbitrary vertex or source vertex, whatever it may be. You can consider any vertex as starting vertex. You can arbitrarily select vertex as starting vertex, any vertex. Either you can select A, B, C, D, S or T. Then here in this example, I am selecting S. S is I named one more edge is the E and F. Then I replaced E with S and F with T. Then S means source and T is termination or destination, whatever it may be. Okay, na? Now in this diagram, I am selecting S is the source vertex or starting vertex now. Okay, na? Then what is the formula? What is the procedure now? From the existing vertex, now immediately include S into spanning tree. So from the included vertices in the spanning tree, identify which edges are possible, which edges are there in the graph. Out of those possible edges in the graph, select minimum cost edge. Now from S, how many edges are there? S to A edge is there in the graph, S to C edge is there in the graph. Then our ultimate goal is apply greedy method. Greedy method means greedy always applying the criteria as min. So, okay, then select either min or max based on problem nature. Here problem nature is minimizing the total cost. So here min is the criteria. Then select S to A, select S to A edge. Then include this edge into spanning tree. Now we got two vertices in spanning tree, S and A. Okay, S and A. Now after including A, now S and A are immediately update edges vertex set in the spanning tree. Now vertex set containing S and A, and all the remaining vertices are there in non-included group. Okay. Now next, from the existing vertices, now existing vertices in the spanning tree are S and A. Now from S and A, what are the possible edges in the graph? Identify. So one edge is S to C, cost is 8. Another edge is A to C, cost is 3. Another edge is A to B, cost is 6. Then what is the criteria here? Always the criteria is min. So select the minimum cost edge among these. So there are 3 edges possible by using S and A. One is S to C, another one is A to C, third one is A to B. Okay. So out of these 3 edges, select minimum cost edge now. What is the minimum cost edge? A to C is the minimum cost edge. Is it clear now? A to C is the minimum cost edge. Now I included C also into spanning tree vertex set. Spanning tree vertex set. Okay. I've included vertex C into spanning tree vertex set. Now spanning tree vertex set is containing SAC. SAC. Now again the same step we need to repeat. From SAC, construct all the possible edges which are not yet included into spanning tree. That means out of spanning tree, whatever the edges that are remained in the graph, select all the possible edges and find out which edge is minimum. Which edge is minimum? SAC is already included. Non-included vertices are BDT. Now A to B is one edge, C to D is one edge, C to D is one edge. We cannot consider C and S because those two are already there in spanning tree. If we include, it makes cycle. If you suppose even that particular edge cost is 2 units, we cannot select C to S because C and S are already there in the spanning tree. We must select an edge in such a way that edge must contain one vertex is belonging to already included vertices set, and another vertex must not belong to already included vertices set. By using this particular criteria, we can select all the edges. So S and C are already included. We cannot take S and C edge. Okay. Then consider A to B, C to B, C to D, because B and D are not included into spanning tree. Not yet included. A and C are included. Then construct all the possible edges from SAC, but there is no possible edge from S because only one edge is possible, that is S to C. S and C are already present in spanning tree. So how many edges are possible now? 3 edges. One is A to B, another one is C to B, third one is C to D. So out of these 3 edges, which edge is minimum? C to D is minimum. C to D is minimum. In this, C to D is minimum. Then immediately include D also into spanning tree. Then construct that edge. Now up to this, we have included S to A edge, A to C edge, C to D edge into spanning tree, and S, A, C, D are included into spanning tree a vertices set. Okay. Now apply the same criteria. Again, select the edges which are containing one vertex is belonging to spanning tree set, vertices set, and another vertices set is belonging to non-included vertices set. Now the included vertices are S, A, C, D. Then what are the possible edges now? A to B is possible, C to B is possible, D to B is possible, D to T is possible, because D, C, A are already there in spanning tree. Then non-included vertices are B and T only. Then construct all the, select all the possible vertices between A, C, D and B, T. So possible edges are A to B, one edge, C to B, one edge, D to B, one edge, D to D, D to T, and one edge. Then how many edges are there? 1, 2, 3, 4, 4 edges. So out of these 4 edges, what are the minimum cast edges now? There are 2 minimum cast edges. One is D to B, another one is D to D. Same cast. Then you can, first time you can select one edge. If you select D to B, now B is also included into spanning tree. Then only one vertex that is out of spanning tree, that is T. Then there are 2 possible edges. One edge is from B to T, another edge is from D to T. B to T edge cast is 5 units. D to T edge cast is 2 units. Okay. Then include D to T, D to T. Then every time verify how many vertices are included till. So if number of vertices are equal to the number of vertices in the graph, then simply stop the procedure. Then whatever the construction that is remained now, that construction is treated as minimum cast spanning tree. Minimum cast spanning tree. Okay. So in this way, we can construct a spanning tree using Prim's algorithm. So what is Prim's algorithm? Prim's algorithm is always following min as criteria. This min as criteria is there in greedy. We are applying greedy approach, that to consider min as criteria. Always select minimum cast edge among all the edges which are possible to reach from already included vertices to non-included vertices in the already included vertices in the spanning tree to non-included vertices in the spanning tree. Okay, na? So like that, follow the same criteria and construct spanning tree. This spanning tree is called as minimum cast spanning tree because every time we are applying min as criteria for selecting next possible edge. That's why whatever the spanning tree that is remained, we obviously we select that particular spanning tree as minimum cast spanning tree. Then what is the cost of spanning tree now? Simply include all the edge casts or add all the edge casts. Then 7 plus 3 plus 3 plus 2 plus 2. 10, 13, 15, 17. So 17 is the spanning tree cast. Okay, the 17 is the spanning tree cast. Now see, the cursor is pointing. This is the spanning tree. The spanning tree cast is 17 units. 17 units. How many edges are included? 5 edges. How many vertices are there? 6 vertices. What I told you, the definition of spanning tree. The spanning tree is containing all the vertices of a given graph, but the number of edges must be one less than the number of vertices. Number of edges must be 1 less than number of vertices. Number of vertices are 6. Now included edges are 5. Now now this is satisfying a spanning tree property. Even you include any edge to this particular spanning tree, that edge makes cycle. We should not have cycle. We should not have more than number of vertices minus 1 number of edges. Now whatever the spanning tree we got, that spanning tree is called minimum cast spanning tree now. Okay, thank you. In the next video, I will explain Driscoll's algorithm for constructing spanning tree, but both behave same. If you take the same graph, that's from the same graph we get same cast of spanning tree. Even Prim's produces 17 units spanning tree cast, then Driscoll's also produces 17 units spanning tree cast, but the way constructing spanning tree is different in Driscoll's algorithm compared to Prim's algorithm. Thank you so much. In next video, I will explain Driscoll's algorithm for calculating minimum cast spanning tree.